When building quantum systems, one of the biggest challenges is scaling up quantum computers to thousands or millions of qubits while maintaining high fidelity. This challenge is not limited to merely increasing the number of qubits, but requires a solution that does not exponentially increase error rates or noise. Simply put, the engineering of large-scale quantum systems that can maintain quantum coherence over extended operations is still an open question. Practically speaking, if this problem can be solved, it would allow qubits to sustain superpositions and entanglements for extended periods of time, while enabling error-free execution of complex algorithms. It would also allow for the creation of fault-tolerant quantum computers with millions of reliable qubits. The result would transform computing, granting humanity the ability to answer currently impossible problems in medicine, cryptography, and optimization. It would render classical systems obsolete in certain domains and drive hybrid quantum classical innovations across industries. Over 12 years ago, while exploring Marco Rodin's vortex-based mathematics for the first time, solving this challenge of coherence and scalability in quantum computers was not on my mind. But after more than a decade of research, I believe overcoming this obstacle is not only possible, it is within reach and will have a long-lasting impact. How I arrive at this hopeful conclusion is via the following diagrams and their interpretation. These are two-dimensional representations of a coherent collection of residues modulo 9. These 17 number maps are built with frequencies in mind and appear to be capable of handling longitudinal and transverse waves. In addition to being a coherent collection of residues modulo 9, these diagrams have another special property that is not readily apparent. They are scalable, and not just a little bit. They appear to be infinitely scalable. Using number theory and an abstract view of calculus, they are mathematically representing cyclical completions that generate surface integrals with no net loss or gain over the whole of the system. This implies there is zero information loss within this quantized system. Numerically, it is mathematical perfection with zero errors and contains no noise whatsoever. The patterns contained within them appear to be chaotic at first glance, perhaps even random. However, nothing could be further from the truth. They are formed from simple sequences, basic repetitions, and elementary numerical designs which align to create an information-based tapestry. The numbers weave together, synchronize, and harmonize in an abstract symphony. One that appears to suggest quantum coherence and infinite scalability are not just dreams within the minds of scientists, but are seen to be manifestations in the physical world if this theoretical solution truly applies to quantum technologies. So what makes information coherent? Is it a special pattern within the information? Is it something more? Perhaps it's easier to describe the opposite first. What is incoherent information? When someone speaks incoherently, their words are random, without a specific purpose in mind. We might even say they're rambling on. We just want them to get to the point. Using this as a framework, we see that coherent information should contain the following properties. The opposite of random is 1. It should be highly ordered. The opposite of purposeless is number 2. It should have a well-defined or calculable value for all instances within the information. And the third and final one is the opposite of an indefinite path to determine an outcome. In other words, there should be a boundary and a finite metric by which we can measure success or failure. Within each of the 17 number maps, there are consistent incremental patterns along every row every column, and every diagonal. They are highly ordered and not random. In this one, we see 1 through 9 repeated in order going up and to the left and down and to the right. These are the longitudinal waves. The transverse waves are surface integrals. Despite the many numbers in the map, they align as individual values and as a systematic whole. This equates to local harmonization and global harmonization of frequencies. The next question to answer is this: do they have a well-defined or calculable value for all instances within the information? The simple answer is yes. Every number is known within the arrangement. There are no infinities within the grid. The third and final condition is shown through the finite nature of the number map. Because the opposite sides of the map can be connected to form a torus, we guarantee there is a boundary condition at all times. This is not an infinite plane, and yet these toroids are infinitely scalable. Scalability is the method by which we can take something and produce it at a different size. When we're talking about scalable information, whether it's at the macro or the micro scale, information that is scalable can change sizes and maintain its coherence. The same patterns and definitions we applied to make the information coherent in the first place should be present at all scales. Scaling the number maps is as simple as tessellating them. In this respect, they are acting like a fractal. In closing, while scaling quantum computers to thousands or millions of qubits that maintain high fidelity is a major challenge, it does not appear to be impossible if the mathematical theories offered in this video hold true. Solving this issue would enable sustained quantum coherence, allowing error-free execution of complex algorithms and the development of fault-tolerant quantum computers with perhaps a limitless number of reliable qubits. Such advancements would revolutionize computing, surpassing classical systems in fields like medicine, cryptography, and optimization, and fostering hybrid quantum classical innovations. These theories offered as a solution deserve the opportunity to be validated and applied where possible for the benefit of mankind. Thanks for watching. If this kind of math interests you, I encourage you to subscribe or comment below. For more information about me and my work, you can check out my website, which is in the description box.